Okay, we'll wait for 10 minutes for others to arrive. I don't know whether someone will be present here or not, but we'll wait for 10 minutes and then we'll start the class of today's session. Okay. Okay, I'm sharing the writing pad also along with the PPT. I hope the writing pad is visible, right? Yeah. Okay, I don't think anyone is going to join today, so I think we should proceed with today's class. I'll share with the first question of today's session. So let me introduce today's like me and today's session itself. So myself Kalpita Nath, and I'm research scholar at IIT Kharagpur, and this is week 8 of heat transfer session, like heat transfer course, and this is a problem solving session regarding to that. This is the week 8 of problem solving session, whose prime instructor is Professor Sunando Dasgupta at Kharagpur. Okay, so without further ado, I'll proceed to the first question of today's session. Actually, there was one question left undone in the previous day, and I'll start with that question itself. Okay, I am sharing the question. Okay, and I'll give you some time to figure out the question, what is happening. So first of all, hot air mass flow rate is given, is passing through an insulated sheet metal duct of diameter 0.15 meter, which is the crawl space of a house. The hot air enters that at the temperature of 103 degrees Celsius, and after a distance of length of 5 meter, it cools down to 85 degrees Celsius. The heat transfer coefficient between the duct and the outer surface and the ambient temperature is 0 degrees Celsius. And H naught is also given. So what we have to do, we have to, like, diagram is also given here and the properties are also given below. So anything you want to use are available there. So temperatures are also mentioned. What is the entrance temperature, what is the exit temperature, and what is the ambient temperature. Okay, so what we have to do, we have to calculate the heat loss from the duct over the whole length L. And the second thing is that we have to determine the heat flux and the duct surface. So this is relatively easy question. So this was remain undone on the previous class. So I'll give you 5 minutes to proceed with this question and then we'll go on with the solution. I hope I am visible and audible. So I think we should proceed. It's enough time is given. Even no students are present here. When you will be looking into the recorded session, I hope you will be given, like you will take that much time which has been allotted to you. Like if I'm telling you to take 10 minutes and if I am turning off the camera, or if I'm giving you some allotted time, that is 10 minutes or 5 minutes, use that time only. And then when I'm starting to discuss the questions, stop your solution and try to see whether you are going on the right direction or not. It's better, even if no one is there in the class. So this videos are like is uploaded on the YouTube channel, right? So and that channel links are been of each videos, individual videos are been shared with you. So try to take that much time that has been allotted. Okay. So let's start with the question of previous days. Like it's question number 13 of previous day. Okay. So for that, first we have to calculate the heat loss. And for the heat loss, we will what we will do? We will do the energy balance equation. Okay. So it's simple. MCP delta T, TML at the end minus Tm naught at the entry. So this is 0.05 kg per second into 1011 joule per kg Kelvin. It's given, right? 1011 joule per kg Kelvin. Okay, CP, yeah, it's given, correct. And then Tm exit is 85, it's given, minus at the entrance the temperature is 103. So it will come out to be minus 910 watt. So if we write this in terms of resistance, this is Hx at L, H naught. This is Ts at L, okay, and this is Tml, and this is T infinity. This is the ambient, right? And this is QSL, okay. So this is the heat transfer coefficient when it is passing through the pipe, right? This is the mean temperature of the fluid, and this is at the surface of the pipe. Like it is in this direction, in the R direction, right? So if this is the pipe, this is the fluid, this is the central line, and this is the ambient. So this is T infinity, TSL, and this is the central line. Okay, this is the pipe, this is the central line, and from here the temperature will change, right? So if this is TSL and this is the TML, mean temperature of the fluid, right? So there will be one resistance through this fluid barrier, and there will be one resistance here. This is for the convection through this the fluid, convection through the air. Okay, so this let us calculate that. This is TML minus T infinity upon 1 upon HXL plus 1 upon H naught. Reynolds number D is equal to 4m dot pi d mu. How? Because m dot is what? M dot is velocity into pi dl, sorry, pi d square by 4, pi d square by 4, not this one, because this is the cross-sectional area, right? Pi d square by 4 and into density. So this V comes out to be this. So Reynolds number is what? Reynolds number is equal to dV rho by mu. Right. So this will come out to be, V will come out to be m dot 4 pi d square rho, and this is d rho by mu. D will cancel out, rho will cancel out. So this is 4m dot pi d mu. Okay, so we'll just put these values. So if we'll put these values, this will be 4 into 0.05 kg per second, pi 0.15 meter dia, into 211.7 into 10 to the power minus 5 Newton second per meter square. This will come out as 20050. So flow is turbulent. L by D is equal to 5 by 0.15 is equal to 33.3. So flow is fully developed. Okay, so L by D is 33.3, right? And 33.3. So what we get from this? We get from this as flow is fully developed, and for the turbulent hydrodynamic entry length, like obviously when there is turbulent flow, there is vigorous mixing in the pipe, so we can consider this as fully developed flow. Okay, despite of any conditions being given. Okay, so Nusselt's number now we'll calculate is given in the equation, which is HXLD by K. So this is 0.23, Reynolds number 4 by 5, Prandtl number 0.3. Correct. 0.23 into Reynolds number is how much? Reynolds number came out to be 20050. So this is 20050. 4 by 5. Prandtl number is how much? Prandtl number 0.698 to the power 0.3. This comes out to be 56.4. Right. So now HXL is equal to 56.4 into K by D. K is 0.0306 and D is 0.15. 11.5 watt per meter square Kelvin. Okay. Now QSL is equal to 85. Okay. Temperature difference upon the total resistance. So resistance 1 is for the inner resistance, and another is outer. So inner resistance 1 is HXL. This is 11.5 plus the external resistance, external heat transfer coefficient 1 upon external heat transfer coefficient, that is 6. Right, this comes out to, this will come out to be 3335. When you will do, you will get this answer. And again, okay, just 1 second. Acha, if we will do for the only the inner area, right, only the inner, we won't consider the outer convection, only the inner convection will consider, then we can get the surface temperature. So this can be written as TML minus TSL. This is the temperature of the fluid media, and this is the surface temperature of the pipe. So this is 1 upon HXL. This is TSL, TML minus QSL and HXL. This is 85 minus 335 watt per meter square, 11.5 watt per meter square Kelvin, 555.9 degrees Celsius. So this is the duct surface temperature. So duct surface temperature is this one. The heat flux is this one. Okay, and watt per meter square, and the one is the heat loss from the duct over time. Sorry, this is the heat loss from the, just 1 second. Yeah, this is the heat loss from the duct over time. Okay, I hope you understood. You don't have any doubt, right? If all of you will check the recorded session, right? If you'll have any doubt, then ask me in the next session. Because it's at a session 8, right? 9, 10, 11, 12. We have 4 more sessions left. So after that, the problem solving session will be over. So I hope you can make the best use of it, because this will help you develop your problem solving capability, and can be even used for your entrance exams like GATE, right? You can easily, like, this is all about practice, so you have to do more and more practice, and these sessions are just to help you out, right? So you, if you will join live sessions, then what you will do, you can directly ask the doubts, you can directly solve here. This will be like 2 hour session, and within 2 hours you can complete everything, like at least one topic that I'll be going with. So it is benefit, is for your benefit only, right? So try to attend the class from next 4 sessions, the last 4 sessions. Okay, so I hope I won't be saying anything more, and I'll be proceeding to today's questions. Just one sec. Okay. So this is question 1 was of today's session. I hope it's visible. Yeah. So what's given? Datas are given, and what is said, that at 1 atmosphere pressure, a thin walled long tube is there of length 2 meter, and at the inlet temperature of the fluid is 100 degrees Celsius. Yeah, a constant heat flux is applied to the air. So air is entering at 1 atmospheric pressure, and diameter of the tube through which it is entering is 5 millimeter, and the length of the tube is 2 meter. And the inlet temperature of the air is 100 degrees Celsius. A constant heat flux is applied. So this is a case of constant heat flux. That the formulas that we have used earlier, same formula will be used here for the air from the tube surface. The mass flow rate of the air is 135 into 10 to the power minus 6 kg per second, and the properties are also given. Choose the closest value for the local heat transfer coefficient at the tube exit. Sorry. So what we have to do, we have to find the local heat transfer coefficient. So I'll give 5 minutes, max to max 7 minutes to solve this. Mm, I'm here only if you if someone join and you have any doubt, do unmute yourself and tell me your doubt. Okay, I'm giving you 5 minutes for this. Okay, so let us, 1 second. I hope I have given you enough time for solving this question. So we'll proceed with the solution. First of all, what is being asked here? We have to find the local heat transfer coefficient. So for that, first of all, obviously for this kind of question, first and foremost thing that we need to do is find the Reynolds number. Okay, so Reynolds number will be dV rho by mu, and here mass flow rate is given. So in terms of mass flow rate, I've already shown you earlier that it will be like 4m dot pi d mu. So this is for mass flow rate is 135 into 10 to the power minus 6 kg per second, and pi into 0.005 meter into 230.1 into 10 to the power minus 7 till second per meter square. Okay, so this will come out to be 1494, that is less than 2300. So the flow is laminar. Cause for we know that for a flow through a pipe, critical Reynolds number is 2300. Just 1 second. Excuse me. Yeah. So now, what we have to do next thing for checking whether the flow is developed or not, we have to find the hydrodynamic and thermal entry length. So hydrodynamic entry length is equal to 0.05 diameter into Reynolds number. So this is 0.05 into diameter is what's given, 0.005 meter. That is 5 mm, right? So this into 1494, this is a Reynolds number. So this will come out to be 0.37 meter. Okay. So now the thermal entry length. This is the hydrodynamic entry length. This is XFTH, hydrodynamic entry length into Prandtl number, right? So this came out to be 0.37 into Prandtl number is 0.69. Yeah. So this will come out to be 0.26 meter. So this, both of them are far less as compared to length, that is 2 meters. So at the exit, the boundary layer is fully developed, right? So the boundary layer is fully developed. So the flow is fully developed and laminar. And here it said that the heat flux is constant. So for heat flux is constant, we have already seen that this equation will be applied. So for constant heat flux, Nusselt's number will be 4.36, right? So for 4.36, Hd by K is 4.36. So H is equal to 4.36 into K by D. So 4.36 into K 0.0338 upon D is 0.005 watt per meter Kelvin meter. So this is 29.47 watt per meter square Kelvin. So which of the option is this? This is option A. I hope I've explained you properly. If you will check the recorded session and if you'll face any problem in understanding, you can ask me out in the next session. Make sure you're available on the next session and do attend the class because attendance counts. Okay, now let us proceed to the next question. So in this question, if the tube surface temperature at the exit, it is linked to the previous question, right? If the tube surface temperature at the exit is 160 degrees Celsius, choose the closest value of the heat rate. So here let me tell you, question number 1 2, 3, 4 are all linked. So question number 2 is also linked to question number 1. So for the question number 2, if the tube surface temperature, the surface temperature of the tube is given, and we have to choose the closest value for heat rate that is entering the tube. Okay, so the rate of heat transfer we have to calculate, and where the external exit temperature, exit surface temperature of the tube is given. So let me give you an idea of how to solve. So heat transfer rate is if in terms of flux we write for Newton's law, from Newton's law of cooling, we know that it is H T exit temperature minus, this is the surface temperature of the fluid, minus the mean fluid temperature, the exit surface temperature of the pipe and mean temperature of the fluid, because this is the direction where the heat will change, heat transfer will take place. So this is one equation, and another equation is this we already have seen in the while we were deriving for flow through a pipe with constant heat flux. We derived the equation in the previous class also. We have solved many questions based on this. So another thing is MCP delta T, Tm naught minus Tmi upon pi dl. This is the surface area. This is the surface area. So this is equation number 2. Now what we will do, will be equating 1 and 2. So what we will get by that? We will get Tm naught is equal to HTS naught plus m dot Cp by pi dl Tmi upon m dot Cp by pi dl plus H. Right, this upon this. You solve this, you will get the exit temperature, and from that you can get the heat transfer rate. Right? And you understood, right, why we have divided it by surface area, because it is the total heat transfer, but heat transfer rate, but if you want to equate both of them, we need to divide it, the heat transfer rate, by the surface area. That's why we have divided by it. So from this we found the mean outlet temperature of the fluid. So if you'll get that, from that we can easily calculate the heat transfer, rate of heat transfer. So this thing you can calculate by yourself, right? So I'll give you 2 minutes to solve this, and then we'll proceed with the further solution of this question. Okay, so let us proceed with the solution then. So I hope you have already solved it, those who are watching the recorded session. So I have already explained how to solve. So here, if we will put all the values, I'm now not going to the details codes, it's already very late. So let me put the values just. So H value is given as 29.47 into temperature is given as 160 degrees Celsius, mind it. Okay. So that's why the final temperature will be in degrees Celsius. This is 135 into 10 to the power minus 6 into this is in kg per second. This is in watt per meter square Kelvin. H, and this is 1014 joule per kg Kelvin, and this is pi into 0.05 meter into 2 meter. This is the numerator. In the denominator, this is 135 into 10 to the power minus 6 kg per second into 1014 joule per kg Kelvin, pi into 0.005 meter into 2 meter plus 24.97 watt per meter square Kelvin. This will give rise to Tm naught in 152.3 degrees Celsius. Correct? Cause the top part, that is numerator, will be watt per meter square Kelvin degree Celsius into degree Celsius, and this will be watt per meter square Kelvin. So this will cancel out and this will be in degree Celsius. Okay. So now what we have to do, we have to find out the heat rate. So the heat rate is Q is equal to m dot Cp Tm naught minus Tmi. This is 135 into 10 to the power minus 6 kg per second into 1014 joule per kg Kelvin. This is into temperature. So Tm naught is 152.3 minus Tmi. What is the mean inlet temperature? Just 1 second. So the mean inlet temperature was 100. So this is 100. So this will come out to be 7.16 watt. So which of the option is? This is option B. Okay. Now let us proceed to the next question. Okay. So if the tube length were reduced to 0.2 meter, choose the correct statement from the following with respect to the value of heat transfer coefficient at the tube exit. So if L is reduced to, length is reduced to 0.2 meter, then what will reduce basically? Now like what will happen if the length is reduced, the boundary layer development will be different, and if boundary layer development will be different, now if we will consider at L is equal to 2, if we will calculate the uh, entry length, so this is for 0.2, that is part C. Let me calculate here. Okay, let me calculate there only. 0.05 for hydrodynamic boundary layer, this is 0.05 DRED, right? So first what we'll do, we'll calculate the Reynolds number. So the Reynolds number for 0.02 is 4 into m dot is 135 into 10 to the power minus 6 into 10 upon pi into Reynolds number will be same. Reynolds number will be because length is varying, the diameter is not varying. So 0.05005 rather 230.1 into 10 to the power minus 7. So this will be this will be what it was earlier. Just 1 second. 1494. Right, this is the Reynolds number. 100. Okay, just 1 second. Okay, just 1 second. This will not be there. I have done some mistake. Okay. Now, what we have to do? We have to find the thermal, hydrodynamic entry length, that is LH, if we'll define it like that. It will be 0.05 into D into Reynolds number. Right, it was 0.05 into D into Reynolds number. Let us check once again. Yeah, 0.05 D into Reynolds number. Right, so this is 0.05 into dia is 0.005 into Reynolds number is 1494. Okay, so this will come out to be how much? This will come out to be 0.37, and thermal entry length dia is same, so it will come out to be 0.26 meter. But now the tube length is reduced to how much? It is reduced to 0.2 meter. So L by D will now change, right? So what will happen? L by D will now change. So now what is happening at the exit? It is 0.37 and 0.26. Now it is reduced to 2. So it the developing it will be fully developed. The flow will be fully developed when it will cross 0.2. So at the exit, it is no longer fully developed, right? So if it is no longer fully developed, the value of the heat transfer coefficient at the tube exit will be greater. Cause see, if the flow is fully developed, it will be like this, right? So at the exit, like if the for the fully developed, there is a mean velocity, right? But when the flow is not fully developed, it will be like this, right? The total boundary layer development. So if it is after some point, it will be like the two boundary layer will mix, and at that point the flow will be fully developed. And before that, the central velocity is more as compared to the velocity. This velocity, the velocity will decrease gradually because the whole the mass flow rate will be same, right? So if velocity here is more, the velocity will keep on decreasing, and eventually zero at the end, right? So the velocity will be more if the flow is not developed. So this is which of the option? That is in case one, the flow is fully developed. So the value of the heat transfer coefficient at the tube exit is greater than that of heat transfer coefficient in 1. So the heat transfer coefficient will also be more. So this is option A. This is option A. This is question number 3, right? Now question number 4. If the flow rate is increased by a factor of 10, choose the correct statement for the following with respect to the value of heat transfer coefficient at the tube exit. This you can easily calculate, right? In the same way you have to do, now the mass flow rate will change, mass flow rate will increase by a factor of 10. I'll give you 2 minutes for this. I hope you are able to solve it. So similar way, first we have to find the Reynolds number. So 4m dot upon pi d. Now Reynolds number will change, right? So this is 4 into 135 into 10 to the power minus 6 into 10, because it has increased by a factor of 10, the mass flow rate. 0.005 into 230.1 into 10 to the power minus 7. So this will come out to be 14940, that is greater than 2300. So what this means, that is the flow is turbulent at the exit. Now if flow is turbulent, L upon D we will calculate, this is 2 meter upon 0.005 meter, that is 400. The turbulent flow at the tube exit will also be fully developed, right? The heat transfer coefficient, so which of the following is that? The heat transfer coefficient, value of the heat transfer coefficient at the tube exit will be uh, exceeding the part in E. How? Because the flow is fully developed, but the flow is turbulent. So obviously, if the flow is turbulent, the heat transfer coefficient obviously will be more. So this is option A. This connected like link question is has ended. Now we'll go for this question number 5. So for any practical situation, if Greshoff's number upon Reynolds number square is far greater than 100, then which of the following is true? Okay, so Greshoff's number represents the Reynolds number, natural convection, and Reynolds number represents the forced convection, right? So obviously Greshoff's number is far greater as compared to Reynolds number, right? So that means the natural convection is far enhanced as compared to the forced convection. So obviously the answer will be option B. An automobile radiator is a device where hot water passes inside a bank of tubes and loss heat to the air. On the outside of the tubes, exterior surface receive heat from the tube walls and transmit it to the air by which of the following? Obviously, it is like if it is extended surface, so it is forced convection, but it is free convection as well. So it is forced and free convection. Now question number 7. Heat transfer by natural convection is enhanced in systems with which of the following? So for natural convection, that is question number 7. For natural convection, Grashoff's number is G beta Ts minus T infinity Lc cube upon mu square. This is the characteristic length, this is the viscosity, kinematic viscosity, this is the temperature difference, this is the temperature of the surface, this is the temperature of the ambient, this is beta, beta is the thermal expansion coefficient, and G is the coefficient of gravity, acceleration due to gravity. Okay, so obviously let us eliminate terms. So low density change with temperature, low density change with temperature. No, this won't come here, right? See, just one second. So coefficient of thermal expansion beta is 1 upon V del T, right? This means we need for increasing natural convection, we need Grashof number more. Grashof number more means beta more. Beta more means this. uh, change in volume with temperature will be more, right? And if change in volume with temperature is more, and with respect to density, okay. So, and with density also it is directly proportional, just minus sign will come. So at constant pressure, so what is happening if it is directly proportional? So density change with temperature should increase in order to increase beta. So D option cancels out. The low temperature gradients, obviously temperature gradient should be high, then only Grashoff's number will be high. So this also cancels out. Then high viscosity means new high. New high means Grashof number low, right? Inversely proportional. So obviously this is also not true. So option true is B. Let us check this also. High coefficient of thermal expansion, obviously high coefficient of thermal expansion. High coefficient of thermal expansion means this. If this will increase, then obviously Grashof number will increase. That is answer is option B. Now let us proceed to question number 8. In a certain heat exchanger, both the fluids have identical values of product of mass flow rate and the specific capacity. That is MCP, that is total C is CPH and CPC. This will be specific heat capacity is same. Now the hot fluid enters at 86 degrees Celsius and leaves at 40 degrees Celsius, and cold fluid enters at 26 and leaves at 55. Assume counter current. Rather, when actually when specific heat capacity are constant for both hot and cold fluid, doesn't matter whether it is counter current flow or co-current flow, right? Though we are still, it is mentioned here that is counter current flow. The effectiveness we have to measure, right? We know the formula for effectiveness, so obviously we can measure. So I'll give you 2 minutes. This is relatively very easy question. So I'll give you 2 minutes to solve this, and we will come up with the solution. Okay. should I solve that for you, or I'll wait for 2 more minutes then for you to solve? I think we should proceed with the solution. This question number 8. Okay. Yeah. Sorry, the sound must be distorted till now. So for the past 5 minutes, the microphone was away. Okay. So for this, let us make this question a bit more understandable or a bit more simple. So we know this diagram. For the heat exchanger, let us consider it counter current flow, like as it is already given. So this is 86, this is 42, this is 26, this is 55. This is outlet temperature of cold fluid, inlet temperature cold fluid. This is inlet temperature of hot fluid. This is inlet temperature of cold fluid. And let me take some other color. Okay. So this is what? This is delta T maximum temperature difference. Now delta T actual is 86, obviously the temperature that is changed in the hot fluid or in the cold fluid as well. 86 minus 42, that is 44 degrees Celsius. Now the delta T the maximum temperature difference. So this will be this one, that is 86 minus 26, this is 60 degrees Celsius. Right, now effectiveness we have to find out. Effectiveness is equal to epsilon is equal to mh dot cph T1 minus T2 mc dot cpc T1 minus T2. This is, sorry, not this, mcp of the lowest value, minimum, T1 minus T1, T1 minus T1. Or we can also write this in terms of cold fluid, that is mc dot cpc T2 minus T1, or this m dot cp minimum T1 minus T1. Now these are equal, mh dot mcp dot and this, so like this is the minimum. Let us suppose if h have minimum value, or both of them are same, right? So this will cancel out. If this will cancel out, T1 minus T2 upon T1 minus T1, that is 44 minus 60 is equal to 0.73. This is option C. Now let us proceed to question number 10. Sorry, 9. A counterflow concentric tube heat exchanger is given as shown in the figure. Oil like is used to cool the lubricating oil. Lubricating oil is in the annular region and water is flowed counter current wise on the inner region. Like the flow rate of the cooling water through the inner tube is 0.2 kg per second, and while the flow rate of the oil on the annulus region is 0.1 kg per second, and diameter of both of them are given. The oil and water enters at temperature, the inlet temperature of oil, that is the hot fluid, is 100 and exit temperature and the inlet temperature of water is 30 degrees Celsius. How long must the tube, that is the outlet temperature of the oil, is given now? How long will it take to cool down? Outlet temperature of the oil should be at 60 degrees Celsius. So how much time will it take? How much time will it take for the temperature of the oil to cool down? The Nusselt's number for the turbulent flow is given here, and for the annular region also we'll take this Nusselt's number. So yeah, you can proceed on solving this. I'll give you 5 minutes for this. Okay, so we have taken enough time in this question. So let us proceed with the solution now. So for this, first of all, what we'll do, what is asked here? How long will it take? The first, what we'll do, we'll calculate the overall, we'll do the overall heat balance and we'll get heat transfer rate from there. So mh dot cph for hot fluid we are taking Thi minus Th naught. So this will be 85. So Th naught minus Thi minus Th naught, correct. So 80, this is point, just 1 second. This is 0.1 kg per second into 2131 joule per kg Kelvin into 100 minus 60 degrees Celsius. This will come out to be 8524 watt. Now, water, this is for oil. Now, water outlet temperature. This is Q is equal to mc dot Cpc Tc out minus Tc in. So, this is 8524 upon mc dot Cpc. Mc means 0.2 kg per second. This is watt. This is 4178 joule per kg Kelvin plus 30 degrees Celsius. So this is Tc naught. This will come out to be 40.2 degrees Celsius. Now, what we can do, area we know, right? Area we know, area is equal to surface area is pi DIL for inner surface area. Now, log mean temperature difference is equal to Thi minus Tc naught. How? Thi, Th naught, Tci, Tc naught. Thi minus Tc naught minus Th naught minus Tci upon ln Thi minus Tc naught upon Tch naught minus Tci. 59.8 minus 30 upon ln 59.8 upon 30 is equal to 43.2 degrees Celsius. So the overall heat transfer coefficient is 1 upon Hi plus 1 upon H naught. Now, cause how long it will take if we need to calculate, then we need to calculate we need to calculate just 1 second. How long must the tube be? So for that, that is for length, we need to find out the heat transfer rate we have found out. So we need to find out the overall heat transfer coefficient. Okay. So now overall heat transfer coefficient for the outer surface is found out. Now for water that is running on the inside, like in inner region. So Reynolds number is 4 mc dot pi di mu. This is 4 into 0.2 upon pi 0.025 meter, 725 into 10 to the power minus 6. So this 14050 greater than 2300. Now, if this is the case for the water, the flow is turbulent. So the Nusselt's number, it's given as 0.023, Reynolds number 4 by 5. We have to find out H, right? Prandtl number 0.4. So this comes out to be 90. You can calculate that later on. So if this comes out to be 90, H inner is equal to Nusselt's number K by Di is equal to 90 into 0.625 upon di, 0.025 meter. So this will come out to be 2250. Now for the outers, like annular region for oil, we need to find out the hydraulic diameter. So hydraulic diameter is equal to d naught minus di is equal to 0.02 meter. Okay. So now Reynolds number for the oil, we need to, for the oil also we need to find out the H, like for overall heat transfer we need to HI we have found out, and H naught we have to find out. So for finding out H naught we need to find out the Nusselt's number, and for Nusselt's number we need to find out the Reynolds number for the oil. So for the oil it is rho UMD H, this is hydraulic diameter, into sorry, upon mu. So this is this will in terms of mass flow rate, this is mh dot pi d naught plus di mu. So this will come out to be 56, that is less than, far less than as compared to 2300. So this is this is far less than 2300. So now for the annular region the flow is laminar. So the Nusselt's number is equal to 5.63, that is given, it is already given for the annular region. So this is H naught dH upon K. So H naught will be 5.63 into 0.138 upon 0.020. This is 38.8. So overall heat transfer coefficient is 1 upon 2250 plus 1 upon 38.8. This is 38.1. Right? Watt per meter square Kelvin. Okay. Now we have to find out the heat transfer rate of heat transfer. So this will be pi the DIL. This is between YTI, cause the heat transfer takes place between water and oil. So this is pi DIL, the surface area, into the overall heat transfer coefficient into delta TLM. So this L we need. This L is equal to Q upon U pi DI delta TLM. So everything we know, this 8524 watt upon 38.1 watt per meter square Kelvin. This we already found out, into pi into 0.025 meter into 43.2 degrees Celsius. This will come out to be 65.9 meter. You understood this, right? So there is no problem in understanding this. Now let us proceed to question number 10. So for question number 10, water flows at a rate of 65 kg per minute through a double pipe counterflow heat exchanger. Water heated from 50 degrees Celsius to 75 degrees Celsius by an oil flowing through the tube. Okay, the specific heat of the oil is 1.780 kilojoule per kg Kelvin, and the oil enters at 115 degrees Celsius and leaves at 70 degrees Celsius. The overall heat transfer coefficient is also given as 340 watt per meter square Kelvin. Calculate the following. One is the heat exchange area we have to calculate, and the rate of heat transfer we have to calculate. Okay. So for this, it's given that the hot fluid here is oil and the cold fluid is water. So the hot fluid temperature, inlet temperature is like it's 115 degrees Celsius, and outlet temperature is 170 degrees Celsius. It's already given. For cold fluid, inlet temperature is 50 degrees Celsius and outlet temperature is equal to 75 degrees Celsius. For the cold fluid, mass flow rate is given as 65 kg per minute is equal to 65 upon 60 kg per second. So this is 1.08 kg per second. Right. For this is for water. For oil also, mass flow rate is mass flow rate is not required. Like here, mass flow rate and Cp together it's given, right? Specific heat is given. So this is Cph is given. So this is 1.780 kilojoule per kg Kelvin. Hmm? Okay. For water, let me give you for water the MC, sorry, CPC. That is the specific heat for water. This is 4.186 joule per kg Kelvin. Okay. So this is CPH is given, MH is not given, right? We have to find that out. Hmm. Mm. Okay, so we can easily find that out, no problem. Uh, we can take, we don't need this even. For cold water, everything is given. We can use that for calculating the heat transfer rate. And for heat transfer rate, overall heat transfer coefficient is given. If we calculate the LMTT, that is log mean temperature difference, then we can easily calculate the heat transfer area. So I'll give you 2 minutes to solve this. This is a very easy problem. The ones you have solved till now are like from that you will get the idea obviously of solving this. Okay, I'll give you 2 minutes. Okay, shall we start with the solving of this question? So first we'll need heat transfer rate. So heat transfer rate is mc/cpc. For we'll use cold fluid. Anything we can use. For hot fluid, everything like the mass flow rate is not given. So for hot fluid is not given. So for cold fluid is already given. So that's why we'll be using this. T2 minus T1. 1.08 into 4186 into 75 minus 8. This is 113 into 10 to the power 3 watt. Now, Q is also overall heat transfer coefficient, like surface area, and delta T log mean temperature difference. So, delta T log mean temperature difference is equal to T1 minus T2. T1 minus T2 minus T2 minus T1 upon ln T1 minus T2 upon T2 minus T1. This is 28.8. So area will be Q upon U delta T log mean temperature difference. This is 113 into 10 to the power 3 watt, 340 watt per meter square Kelvin into 28.8 degrees Celsius. This will come out to be 11.54 meters square. Okay. I hope there is no problem in understanding this question. This is the last question we'll do for today. We have 2 more questions, but it's already 3 more questions actually, but it's already very late. So we'll do 1 more question and there's 3 we'll do next. So for this question, hot chemical product, that is hot fluid basically, it is at 600, it comes at 600 and has flow rate of 30 kg per second, are used to cool down the chemical products that has mass flow rate of 200 kg per second, and the cold fluid is entering at 200 degrees Celsius, right? The total heat transfer area is given as 50 meters square and the overall heat transfer coefficient is given as 1500 watt per meter square Kelvin. Right. Calculate the outlet temperature of the hot and cold chemical products. Parallel flow heat exchanger is given here. Right. So for parallel flow, the graph is also given for calculating the effectiveness for corresponding NTU. Right. So if we know NTU, and also if we know C minimum upon C maximum, that is the specific capacity, heat capacities of maximum, minimum to maximum, then we can calculate the corresponding effectiveness, right? The properties are also given here. So I'll give you 5 minutes because we don't have much time. I'll give you 5 minutes to solve this and then we'll proceed with the solution. Okay. 5 minutes, no, 2 minutes. Okay. So for this, the heat capacities, that is CH is capital CH is MECPH. This is 30 into 2.5. This is for the hot fluid, right? So this is 75 kilowatt per Kelvin. For cold fluid, this is MCCPC. This is 28 into 4.2. This is 117.6 kilowatt per Kelvin. Now, from the graph, we also need C minimum upon C maximum. So C minimum upon C maximum is equal to 75 upon 117.6. So this is 0.64. So this is NTU. NTU we need to find out. This is UA upon minimum, C minimum. This is 1500 into 50 upon 75 into 10 to the power 3. This is 1. So for NTU 1 and for C 0.64, this will come across 0.4 0.48, yeah. This will come out to be approx 0.48. So your value should also be similar, like almost close enough. So we know that epsilon is equal to actual heat transfer upon maximum possible heat transfer, right? So this is MHCPH TH1 minus TH2 upon C minimum TH1 minus TC1. Right. So this is TH1 minus TH2 upon TH1 minus TC1. This will come out to be, this is 0.48, 600 minus TH2 we don't know, and 600 minus 100. Cause for finding out the outlet temperature, we need to do this, like TH2 we need to find out. TC2 we already, TC2 we need to find out, right? Yeah, TC2 we don't know. TC2 also we'll find out. Just wait. So from there we found out that TH2 is 360 degrees Celsius. Now the heat lost by hot fluid is equal to the heat gained by cold fluid. So this is MHCPH TH1. The heat transfer will be equal, na? So TH2. This is MCCPC TC2 minus TC1. This is 75, 600 minus 360 is equal to 117.6 TC2 minus 100. So from here TC2 will come out to be 253.06 degrees Celsius. So this is answer of this question, is all that has been asked. I'll show you the next question for 2 minutes, and I hope you will solve this as like this. This is the question number 12. For the next 1 minute, I'll show you the next 3 questions, and I hope you will solve this at home as homework, and we'll discuss about this in the next class. Okay. This is 12. This is 13. This is 14. Okay. Now I'll end the class here. We'll discuss this questions in the next session. Okay. Bye bye. I hope all of you have enjoyed today's class, and who have not, all of you who have not joined, you go on with the recorded sessions and take that much time that has been allotted in between any questions, and try to solve this, and then check like what I have discussed, check with that whether you have undergone the same process of solution or not. Okay, I'll see you in the next class. Bye bye.